Hello, in this lecture we'll find out the length of chord PC. In the drawing we have a semicircle. Inside this semicircle, we know that the center of the semicircle is at point O. Inside this semicircle we have square DEFO, this square, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of chord CB. Okay, so first of all we know that the area of square ABCD is equal to 5 units. So here you can write down that the area of square DEFO the two square brackets is the sign for the area. So the area of square DEFO is equal to 5 units. And we know that the area of any square is equal to the side squared. Because of the fact that all the sides of the square are equal to each other, the area of any square is the side, one side squared. Therefore, the area of square DEFO that is equal to 5 square units is equal to the side squared. We will take a root out of this equation and find out that the side here equals the side of one square, one side of square ABCD, DEFO equals to the square root of 5 units. Okay, so I can write down here that FO equals to the square root of 5 units, EO also equals to the square root of 5 units, DE equals to the square root of 5 units, and finally DF also equals to the square root of 5 units. We also know that all the angles inside any square are right angles, therefore all those 4 angles are right angles. In the next step, we'll join points D and O together by a straight line. Point O is the center of the semicircle, point D is the point of the semicircle itself, therefore DO is the radius of this semicircle. In addition, DO is not only the radius of the semicircle, but it is also, if we focus on the right triangle DFO, this right triangle, it is the hypotenuse of the right triangle DFO. So I copy the right triangle DFO in a new page, and we will implement the Pythagoras theorem on this right triangle DFO. Okay. this is the right triangle DFO. It's a copy from the original drawing. We've already found out that DF is one side of square DEFO, that is equal to square root of 5 units, and FO, for the same reason, it is also equals to square root of 5 units. So our mission is to find out the value, the length of the hypotenuse DO. DO is the hypotenuse of triangle DFO, the right triangle, and it is also the radius of the semicircle. So here we'll implement the Pythagoras theorem on the right triangle DFO by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is DO square, and it is equal to the sum of the squares of the perpendiculars. The square of this perpendicular is DF square, and the square of this perpendicular is FO square. And the sum of the square of the perpendiculars is DF square plus FO square. Okay? So DO square equals to DF square. DF equals to the square root of 5 units, and therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square is square root of 5 square. Square root of 5 square is of course 5. So it is 5 plus 5. So if I know the DO square, this is the square of the hypotenuse, equals to 5 plus 5, that is 10. We'll take a root out of this equation, and we find out that DO equals to the square root of 10 units. DO equals to the square root of 10 units. Here. DO is also the radius of the semicircle. So I found out that the radius of this semicircle equals to the square root of 10 units. O is the center of this semicircle. P is the point of the semicircle itself. Therefore, OB is also the radius of this semicircle that is equal to the square root of 10 units. For the same reason, OA is also the radius of the semicircle. Why? Because O is the center of the semicircle and A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to square root of 10 units. In the next step, I will present to you a new rule. Rule number 1, according to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. I will write it down. The sum of the angles on one side of a straight line is equal to 180 degrees. So actually, if we have straight line, this is line segment AB is a straight line, and we take this point K, so if we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. That is to say, this angle equals to 180 degrees. In the lower side, the sum of the angles will also be equal to 180 degrees. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing, we know that this is a semicircle. AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. AB is a straight line. So if we focus on the upper side of the straight line AB, it's point O. On the upper side of AB at point O, the sum of the angles must be equal to 180 degrees. That is to say, this angle plus the missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule number 1. So the missing angle must be equal to 90 degrees also. In order to complete the sum of the angles on the upper side of the straight line AB at point O to 180 degrees, this angle must be equal to 90 degrees. Okay? And because of the fact that angle EOB is 90 degrees, therefore triangle EOB is a right triangle. Therefore we can implement the Pythagoras theorem on the right triangle EOB. So I copy triangle EOB, the right triangle EOB, in the new page, and we'll implement the Pythagoras theorem on this right triangle EOB. This is the right triangle EOB. It's a copy from the original drawing. We have already found out that OE equals to square root of 5 units. OB is the radius of the semicircle that is equal to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So we'll implement the Pythagoras theorem on this right triangle EOB. So by PT, equation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is EB squared, the hypotenuse EB, therefore is EB, therefore the square of the hypotenuse is EB squared, and it is equal to the sum of the squares of the perpendiculars. Here EO is perpendicular, therefore the square of the perpendiculars is EO squared, and the sum of the square of the perpendiculars is plus OB is perpendicular, so the square of the perpendiculars is OB squared. Okay, we found out that EB squared equals to EO squared plus OB squared, so EB squared equals to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10 units, therefore OB squared is equal to the square root of 10 squared. So we found out in conclusion that EB squared equals to the square root of 5 squared plus square root of 10 squared. Square root of 5 squared equals to 5, of course. Square root of 10 squared equals to 10, so it is 5 plus 10. That is to say EB squared equals to 5 plus 10, that is 15. We will take a root out of this equation, and we will get that EB equals to the square root of 15 units. The hypotenuse equals to the square root of 15 units. So we can write here the original drawing that EB equals to the square root of 15 units. Our mission is to find out the length of chord EB. This chord EB, chord CB. We have to find out the length of chord CB. Chord CB equals to CE plus EB. We know that EB equals to the square root of 15 units. The only thing that is left to find is to find out the length of line segment CE. Okay, in order to find out the length of line segment CE, we will complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend side OE of the square in both sides, in the upper side and in the lower side also. We extend OE in the upper side by a straight line until it touches the circle. At this point, we define the touching point of the extended OE in the circle as point M. In the next step, we will extend EO in the lower side until it touches the circle. Okay. We define the touching point of the extended straight line EO in the circle as point N. Here, point O is the center of the circle and the semicircle also. Point N is the point on the circle itself. Therefore, ON, this is exactly the definition of a radius. Therefore, ON is the radius of this circle that is equal to square root of 10 units. We've already found out that is equal to the square root of 10 units. Here, point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of this circle that is equal to the square root of 10 units. And OE equals to square root of 5 units. What is the length of ME? ME equals to OM minus ME equals to OM minus OE. Again, ME equals to OM minus OE. That is to say, ME equals to OM, that is the radius of the semicircle and the circle itself, that is square root of 10 units, minus OE, that is equal to the square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. And ON is the radius of the circle that is equal to square root of 10 units. In the next step, I will present to you a new rule, rule number 2, and we will implement the new rule in our drawing. According to the new rule, this is actually rule number 2. Rule number 2 is true in any circle. So the circle that I'm drawing could be any circle. So if we have chord AB, this is chord AB. That intersects with chord CD. This is chord CD. And the intersection point is at this point. We define the intersection point as point O. So here, if chord AB intersects with chord CD, it's point O. Point O is the intersection point between the two chords. Then the following equation will be true. CO or CO times OD equals to CO times OD equals to AO times OB. Okay, repeat again. If chord AB intersects with chord CD at point O, then CO times OD equals to AO times OB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN that intersects with chord CB at point E. Okay, so I copy again the drawing, only with the two chords that intersect with each other, in order to clarify the things without the other things that are in the drawing. Chord MN passes through the center of the circle. This is chord MN. That intersects with chord CB. This is chord CB. And the intersection point is here at point E. So I write it down in our original drawing. We know that chord MN intersects with chord BC or CB. It's point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. Repeat again. According to rule number 2, you get that ME times EN equals to CE times AB. This is the implementation of rule number 2 in our original drawing. So we have already found out that ME equals to square root of 10 minus square root of 5. We have already found out that EB equals to the square root of 15 units. What is the length of EN? From the original drawing, it is very easy to see that EN equals to EO plus ON. So EN equals to EO, that is square root of 5, plus ON, that is square root of 10 units. In conclusion, you can write down that EN equals to the square root of 10 plus square root of 5. Okay? So here, ME equals to square root of 10 minus square root of 5. En equals to the square root of 10 plus square root of 5. And it is equal to CE, that is the missing line segment, times EB. We will found out that EB equals to the square root of 15 units. Okay. Here we have square root of 10 plus square root of 5 times square root of 10 minus square root of 5. According to the algebraic identity, that A minus B times A plus B equals to A squared minus B squared. Now a specific equation, A equals to the square root of 10 and B equals to the square root of 5. Therefore, A squared minus B squared, A squared is square root of 10 squared, that is 10 minus B squared, B is square root of 5, therefore square root of 5 squared equals to 5, so it is 10 minus 5, that is equals to CE times square root of 15. CE times square root of 15. So here 10 minus 5 is 5. So in conclusion, we found out that according to rule number 2, 5 equals to CE times square root of 15. We divide this equation by square root of 15. And we get that CE equals to 5 over square root of 15 units. Here we found out that CE equals to 5 over square root of 15. Therefore, we know that CB, the coordinate we are looking for, equals to CE plus EB. I'll write it down. CB equals to CE plus EB. Again, CB equals to CE plus CB. We just right now found out that C equals to 5 over square root of 15, and we have already found out that EB equals to the square root of 15. So actually, the answer to the question is that the length of chord CB equals to 5 over square root of 15 plus square root of 15. We'll simplify this expression by multiplying square root of 15 by square root of 15, and then we'll divide it by square root of 15. We can do it because we can multiply anything by 1, okay? In this way we'll have a common factor with this expression. So CB equals to 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. So we actually found out that chord CB, the chord that we are looking for, equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. 5 plus 15 is 20, so CB equals to 20 over square root of 15. We'll multiply this expression 20 over square root of 15 by square root of 15, then we'll divide it by square root of 15 in order to eliminate the square root in the denominator. Okay, so CB equals to 20 over square root of 15 times square root of 15 over square root of 15. So if I found out that CB equals to 20 times square root of 15, square root of 15 times square root of 15 is 15. We'll divide this expression by 5 for the numerator and the denominator, and we'll get that CB equals to 20 over 5 is 4, so in the numerator we have 4 times square root of 15 over 15 over 5 is 3. In conclusion, we found out that the length of chord CB equals to 5 times square root of 15 over 3, or in terms of numbers it is equals to 5, we'll check it here, 5 point 5.164 units. 5.164 units. So the answer to the question is that the length of chord CB equals to either 4 times square root of 15 over 3, or in terms of numbers it is equal to 5.164 units. In the next step I will summarize the lecture. So actually we have here a semicircle. We know that the center of this semicircle is at point O. Inside this semicircle we have square DEOF. And we know that the area of this square equals to 5 square units, and we have to find out the length of chord CB, this chord. So first of all, we know that all the angles inside the square are right angles, therefore those 4 angles, they are all right angles. And we know that the area of any square equals to one side squared. So the area of square DEFO equals to 5 square units. So that is to say the area 5 square units equals to one side squared. We took out of this equation and found out that the side, one side of square DEFO equals to 5 to square root of 5 units. So here all the sides of this square are equal to each other, and they are equal to square root of 5 units. Okay. In the next step, we actually focused on this right triangle. DOF. We implemented the Pythagoras theorem on the right green triangle, DOF. So I copied the right triangle. Here, and we implemented the Pythagoras theorem on this right triangle DFO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DO, therefore the square of the hypotenuse is DO squared equals to the sum of the squares of the perpendiculars. That is to say, it is equals to DF squared plus FO squared. Okay, so DO squared equals to DF squared, DF equals to square root of 5, therefore DF squared equals to square root of 5 units, plus FO squared. FO equals to the square root of 5, therefore FO squared equals to square root of 5 squared. Square root of 5 squared equals to 5, of course, therefore DO squared equals to 5 plus 5, that is 10. So DO squared equals to 10. We took a root of this equation and found out that DO, the hypotenuse of this right triangle DOF, equals to square root of 10 units. Okay. Here, the hypotenuse DO equals to square root of 10 units. But DO is not only the hypotenuse of the green right triangle, but it is also the radius of this semicircle. Why? Because of the fact that line segment DO starts from point O, that is the center of the semicircle, and ends at point D, that is a point on the semicircle itself. This is exactly the definition of a radius. Therefore, DO, that is equal to the square root of 10 units, equals to the radius of this semicircle. So the radius of this semicircle equals to the square root of 10 units. Okay. OB is also the radius of the semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O, and ends at point B. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. For the same reason, OA OA, it starts from point O, that is the center of the semicircle, and at point A, that is the point of the semicircle itself. Therefore, OA is the radius of the semicircle, that is also equal to the square root of 10 units. Okay. In the next step, I presented to you rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. If AB is a straight line, and we focus at point K, if we focus on the upper side of point K on the straight line AB, the sum of the angles must be equal to 180 degrees, according to rule number 1. That is to say, the sum of the angles on the upper side of AB, here it is 180 degrees. The same thing is true in the lower side. Here the sum of the angles is also must be equal to 180 degrees according to rule number 1. We actually can implement rule number 1 in our drawing. Why? Because in our drawing we know that this is a semicircle. AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have on the upper side, at the upper side of AB at point O? We have this angle, it is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees. So actually, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles in the upper side of the straight line AB at point O to 180 degrees, the missing angle must be also equal to 90 degrees. And because of the fact that this angle is a right angle, that is to say angle EOB is a right angle, therefore triangle EOB is a right triangle. This is a right triangle, EOB. So I copy triangle EOB in a new page. This is triangle EOB that I copied from the original drawing. And we implemented the Pythagoras theorem on this right triangle EOB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OB, the hypotenuse of this triangle EOB is EB. This is EB, this is the hypotenuse of this right triangle, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. This is to say it must be equal to EO squared plus OB squared. So according to the Pythagoras theorem, we found out that EB squared equals to EO squared plus OB squared. So EB squared, it is the missing side, it is equals to EO squared. EO equals to the square root of 5 units, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10 units, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared is 5, plus square root of 10 squared, that is 10. That is to say, EB squared equals to 5 plus 10. 5 plus 10 is 15, so EB squared equals to 15. We took a root out of this equation and found out that EB equals to the square root of 15 units. Here, EB equals to the square root of 15 units. So we can write down in the original drawing that EB, here, EB equals to the square root of 15 units. Okay? In the next step, we made the construction, we completed the semicircle to a circle, and then we extended line segment OE in both sides by straight line. This is to say we extended OE to the upper side until it touches the circle at point M. We defined the touching point of the extended OE and the circle as point M. Then we extended EO until it touches the circle at point N. Point N is the touching point of the extended EO and the circle. Okay. Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. What is rule number 2? According to rule number 2, if chord AB, this rule is true in any circle, so this circle could be any circle. If chord AB intersects with chord CD at point O, point O is the intersection point between the two chords, then according to this new rule, AO times OB equals to CO times OD, or CO times OD equals to AO times OB. Okay? We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, so here I copied again the drawing before the other things, only the two chords that intersect with each other. Again, chord MN intersects with chord CB at point E. Therefore, according to the new rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. ME times CE equals to CE times EB. We've already found out that ME equals to the square root of 10 minus the square root of 5. EB equals to the square root of 15 units. And EN equals to EO plus ON. That is to say, EN equals to EO, that is square root of 5 units, plus ON, that is square root of 10 units. In conclusion, we found out that EN equals to square root of 10 plus square root of 5. Okay, and then ME equals to the square root of 10 minus square root of 5 times EN, that is equal to square root of 10 plus square root of 5, and it is equal to CE, that is the missing line segment, plus EB. We have already found out that EB equals to the square root of 15 units. Okay, according to the algebraic identity, A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to the square root of 10 and B equals to the square root of 5. Therefore, A equals to square root of 10, A squared equals to 10. B equals to square root of 5, therefore B squared equals to the square root of 5 squared, that is 5. Therefore A squared minus B squared equals to 10 minus 5. That is equal to CE times square root of 15. 10 minus 5 is 5. So in conclusion, we found out that 5 equals to CE times square root of 15. Here we divided this equation by square root of 15. We found out that CE equals to 5 over square root of 15. Okay? Here, CE equals to 5 over square root of 15. We are looking for the length of chord CB. From the drawing, it is very easy to see that CB equals to CE plus EB. Okay, CB equals to CE plus EB. Again, CB equals to CE plus EB. That is to say, CB equals to CE, that is 5 over square root of 15, plus EB, that is square root of 15. Here we multiplied square root of 15 by square root of 15, then we divided by square root of 15. Actually, we changed nothing because we multiplied it by 1. It is allowable. In order to overcome a factor with this expression, and we got that CB equals to 5 plus square root of 15 times square root of 15 over square root of 15. Again, CB equals to 5 plus square root of 15 times square root of 15 over square root of 15. So CB equals to 5 plus square root of 15 times square root of 15 is 15. So in the numerator we have CB equals to 5 plus 15. In the numerator we have square root of 15. 5 plus 15 is 20. So in conclusion we found out that CB equals to 20 over square root of 15. Then we multiplied this expression by square root of 15 and then we divided by square root of 15 in order to eliminate the square root in the denominator. Yeah, we multiplied by square root of 15 and then we divided by square root of 15, so we changed nothing. So in the numerator we left with 20 times square root of 15. In the denominator we have square root of 15 times square root of 15, that is 15. So in conclusion we found out that CB equals to 20 times square root of 15 over 15. We divided both the numerator and the denominator of this expression by 5. 20 over 5 is 4 and 15 over 5 is 3. So in conclusion we found out that CB, the line segment, the chord that we are looking for, CB equals to either 4 times square root of 15 over 3, or in terms of numbers, it is equal to 5.164 units. So the answer to the question is that the length of chord CB, the chord that we are looking for, the length of this chord CB equals to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equals to 5.164 units. Okay, thank you very much.